Hi, everyone. So let's talk about factorials. Do you see the n factorial button on your calculator? On some TI calculators, you might need to look under the PRB or probability menu, and you may see an exclamation point. N factorial, not n excited or n yelling, n factorial, all right? And it's often used to describe sequences as part of formulas for sequences or series. For example, in the series expansions for sine of x and cosine of x, you'll use factorials in the denominators. All right, now we define 0 factorial to be 1. That makes everything work out. If n is a positive integer, if n is in the set z plus, then n factorial is the product of the integers from 1 to n. So if n is big enough, then you can do the whole dot, dot, dot thing here, right? You can do a count up. N factorial is 1 times 2 times 3 times da 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 times n, or count down. N factorial, you can start with n and then subtract by 1 each time, n minus 1, n minus 2, and so on, down to 2 and 1, basically reversing this list of factors. N here, 2 here, 1 here. All right. Examples. 0 factorial is 1, remember? That makes the formulas consistent in this section. 1 factorial is 1. 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1, or 6. 4 factorial is 4 times 3 times 2 times 1, or 24. Now take a look here. From 1 factorial to 2 factorial, we multiply in the 2. From 2 factorial to 3 factorial, we multiply in the 3. And guess what? To get from 3 factorial to 4 factorial, to get from 3 factorial to 4 factorial, you multiply in the 4. All right. And that's going to be a recursive way of developing the list of factorials. We'll talk more about recursion later on. Okay, so what if we wanted 5 factorial? Well, yeah, it is 5 times the rest of this. Okay, that's exactly the point. It's 5 times all of this, right? It's 5 times all of this. So it's going to be 5 times 4 factorial. Okay, 4, just as 4 factorial is 4 times 3 factorial, 5 factorial is 5 times 4 factorial. Basically, you bring in the next integer to get the next factorial. Factorial is at the same level of as exponentiation in the order of operations, in the sense that they both represent successive multiplications. So 2 cubed, right, is 2 times 2 times 2, right? Whereas something like 3 factorial would be 3 times 2 times 1. They represent successive multiplications, and they're each at the same level on the order of operations in terms of the order you work an expression out. All right, so the factorial binds more tightly than the multiplication operator. That's why here I can write 4 factorial equals 4 dot, or multiplied by 3 factorial, right? Because even in the absence of grouping symbols, it's automatically assumed that the 3 factorial binds tightly, right? Then you multiply in the 4. Still, if this makes you feel more comfortable, be my guest. Speaking of the recursive definition of the factorial function, remember 0 factorial is 1. And then to get the new factorial, n factorial, you take the previous factorial, n minus 1 all factorial, and multiply by n. Like here, this is the case where n equals 4. To get 4 factorial, you take the old factorial, bring in the new number. Again, to get n factorial, take the old factorial, bring in the new number, the new integer. Again, this is called a recursive definition of the factorial function because it describes how previous values determine later values. Okay, it's like climbing a ladder. All right. Next time, we're going to apply factorials to counting. I know how to count. Are you sure? If you've taken Math 119 statistics, maybe, but counting is harder than you think. Next time.